I think we will actually finish the module today. But anyways, I think we have a test coming up next week.
Yes, we do on Thursday.
True. Yeah. Next week.
Oh, okay.
I mean, you don't have to take any of the tests, technically, so it's part of your grade, but, you know. We could talk about it. Let's just not plan on even having any emergencies.
Oh man, I think I got an emergency.
Yeah, you can't really plan emergencies in advance. That sort of would be the
I see it.
antithetical to the emergency. But emergencies happen. I understand that. All right.
You notice he's going to talk about the probability of car accidents.
Yes. Yeah. I think we'll be okay for the exam. Module 5 is very short. There's just a little bit, just a couple of things we're going to get into in Module 5, not much. So yesterday we left off talking about counting, and so I was showing you different counting strategies, and basically, you know, the rule was essentially the first question you have to decide right is that are repeats allowed? So are repeats allowed, or in other words, is replacement allowed? Another, you know, are you allowed to pick the same thing more than once? And that was like the license plate example. Like on a license plate, you could pick the same number 3 times to throw on a license plate. It's not a problem. Your license plate could be 1111, no problem. And so if repeats are allowed, then you have to just go with the basic counting rule. And that's where essentially your only choice is you just have to think about, okay, how many ways could all of these things happen, and then multiply them all together. You know, there's 26 ways to pick this letter and 26 ways to pick that letter. And actually the basic counting rule will work no matter what. But if repeats are not allowed, in that case, we can use a couple shortcuts. So this would be like the example of, like, if I'm putting books on my shelf, I can't put the same book in 11 different slots because it's a physical book. Once I put it up, it's stuck. I can't pick it again. Or if I'm sampling people, I can't sample you more than once because then you don't count as multiple people. And so if repeats are not allowed, then all you have to ask yourself, does the order matter? Because if the order you get picked matters, then you're dealing with a permutation. And if the order is not important, so if you don't really care if you get picked first, second, third, fourth, or whatever, then you're dealing with a combination. And those are the 3 types of counting problems that we looked at yesterday. All right? Hopefully that seems vaguely familiar. All right. Then from there, sometimes you might have to combine counting strategies, which we'll see, but also counting strategies can make some probability problems easier to think of them as counting problems. Because remember, the most basic definition of probability is like the number of ways something can happen divided by the number of possibilities. Well, those are counting questions. How many ways can something happen? That's a counting question. All right. So you may have to combine counting strategies. Here's an example. So let's say that you have a pool of people, and you have to pick 12 jurors, and 15 of them are male, 10 of them are female, and what I would like to know is how many ways could you pick that jury so that you end up with an even split, 6 men, 6 women? All right. This is a counting problem because this is right. That's how many ways, right? That's essentially telling me I'm doing a counting problem, and so. When I'm starting to think about counting problems, first thing I do is I go back and I think about my tree diagram, and you think about, well, what's the first thing you need to know? Are repeats allowed or not when you're picking jurors? You can't pick the same juror more than once because then you're never going to fill your jury, right? They only count as one. So repeats aren't allowed, so I know I don't have to go down that route. Repeats aren't allowed. Now the question is, does the order you get picked to be put on the jury matter, or does it not matter? It doesn't matter because you're in or you're out. So I know for a fact I need to be using combinations somehow. This one's a little more complicated, though. Why? Because there's 2 pools of people. Okay, and so what happens is we need to treat them separately first, right? So there's 12 jurors, and I want to have an even split. So I would like to have 6 men. They don't have to be in order like this, right? I'm just doing it for the purpose of display. But 6 men and 6 women. That's what I'd like to see. Okay, well, how many ways can it happen? Well, we could think about each one separately. So, for example, there's a lot of ways I could pick my 6 men. In fact, how many ways are there?
5,500.
How do you know? Yeah, so we can think about over here, I got to pick 6 men to get an even split, and I have 15 men to pick from. I can't replace them. The order doesn't matter. So on this side, we could do, there's 15 men, and I have to pick 6 of them, right? That would give us, so we could figure that out. You could do it separately. So you could go 15C6. So right in your calculator, you just go 15, go find your NCR button, plug in 6, hit enter, and then that's how you got 5,005, right?
How would you write that another way?
What's that? Yeah, if you wanted to do it as if you wanted to do it by hand, that would be 15 factorial over 15 minus 6 factorial times 6 factorial on the bottom. And you'd have to hash that out. I don't really recommend doing it that way, but you could. That's the formula, though. So there's 5,005 ways to pick the men, it looks like, right? It's a combination because the order doesn't matter. And then same with the women, though. There's a lot of ways to pick the females, right? Because there's 10 of them, and I want 6 of them. All right? So then you could do 10C6, and then that would just, in your calculator, 10 NCR6. What does that get you? 210. Now, there's a certain number of ways to pick the males. There's a certain number of ways to pick the females. But what do we got to do? We got to do them both, right? So in this case, the combinations work for the men and women separately. But to figure out the number of ways they interact, the basic counting rule tells us that we should multiply them. Yeah. So the answer here is we need to take 15C6 times 10C6, because this is number ways men, and this is number ways women, and then we multiply them. In this case, the numbers didn't actually get that big, so we could pull them out separately. So you'd multiply those two numbers together, and what would you get?
1051050.
Like that?
Yeah.
Other people get that? Yeah? Did anybody else get that number? So I can just confirm it. Okay, perfect. I just wanted to confirm. Yeah. So a little over 1 million ways that you could get an even split on the jury. So that's all unique juries that have 6 men, 6 women. Yeah? You can actually, sometimes these numbers get really big. So actually in your calculator, if you're reasonably decent at working with a calculator, you could actually just, if you put the combination in parentheses, then you can actually put it all in at once into your calculator. Like that. So you put parentheses around the first combination statement in your calculator, and then do multiplication and then put the second one in parentheses in your calculator.
You can also copy the
Yeah.
equations.
It'll save it. Yeah.
I did it without parentheses and it still went through. Not so much. Will it make a difference in some scenarios?
You got the same answer without parentheses? You put it in just like that without parentheses?
Yeah.
And it came out with that number? That's interesting. Maybe the calculator understands that the NCR is in parentheses. I don't know. Maybe you don't need them. I'd be afraid to say that it'll always work, but maybe it will. Yeah, I don't know. Yep. All right, any questions on this example about why we chose any of those numbers or anything like that? Where the numbers come from? Okay. So in other words, it's like if you've got a big pool and then within that pool you have subcategories and you want to see a certain number from one certain other, we can still tackle it. We just use combinations from each pool separately and then we multiply them together at the end because that's how they interact. So, okay. All right. Now, this is the number of ways. So if I'm saying how many ways, that's a counting problem. I'm going to get a number out of that. But what if I want to know the probability? Let's say if I'm just randomly picking jurors, what's the probability that you get a 50-50 split? See, A counting problem, number of ways, gives us a big number. Probabilities should be between 0 and 1, and you should get it by dividing. So what are we going to divide by? That won't get us a small number because we know the number of ways is like 1 million, so our denominator better be bigger than that. So because remember what's the most basic definition of probability? It's the number of ways to get, right, the 6-6 split divided by what? Yeah, the number of ways that you could just pick the jury, total. Because the denominator in a probability is like everything that could possibly happen. You could get a lot of different juries that were not even splits. Okay. And so now the numerator we already calculated. True? The numerator we just did because there were 15 males and we wanted 6 of those. And there were 10 females and we wanted 6 of those. That's what we calculated in the last part. It's like 1 million and some change. Okay. Now, what's our denominator, though? How many ways could you actually, if we just looked at the denominator, number of ways to pick the jury? Really, what we're doing is number of ways to pick 12 people. Okay. Well, again, can they repeat? No. Does the order they get picked matter? No. It's still a combination problem. But how many are we picking from and how many do we need?
25, 12.
Yeah, so then you look at the overall numbers. So there's 15 males and 10 females. So if I'm just picking a jury without regards to their gender, right, then it's just there's 25 out there and I want 12 of them. Right? And so that would be the number we would divide by. So what does that actually come out to be? It's big. 5200300?
Yeah.
Okay, so 5,200,300. Okay, so that would actually become our numerator or our denominator. So I'm going to put it over here though because you'll see a pattern. Okay, see the numerator we calculated in the last slide. It was the 1,051,050. That's the numerator, and then the denominator we just calculated was this one, right? So we would just take the ratio of those two, and let's round it to 4 decimal places. What do you get if you take that divided by that?
2021.
2021. There you go. So if you were to just randomly select your jury, then there'd be about 20% chance that you'd end up with an even split. So, okay. If you look at the where I wrote it with combinations and stuff, though, you notice there's pattern there, right? What is it?
They add up.
Yeah, so there's 15 men and 10 women in my numerator. Those add up to 25 in my denominator. I want 6 men and 6 women. They add up to the 12 people I have to pick. So then you could actually mess around with it, and you could actually use this as a format. You could really easily figure out, well, what's the probability that I end up with like no females, like no women, right? Well, then I could just put a 0 here. I could swap that out for a 0 and put a 12 right there, and then you figure it out pretty quickly. So this pattern right here, this will work anytime that you're like picking things from like 2 different groups and you want to see like a certain number from one and a certain number of other. You can use this pattern with combinations to help you solve the problem. It makes it a little more straightforward, I think, actually. Okay. Questions about any of those numbers, where they came from, why we did anything with them that we did? You could actually plug that into your calculator. Now this one, I don't know if you could do without parentheses or not, but you could try it. But in your calculator, you could actually you could get the probability right away. It'd be 15 NCR 6 times 10 NCR 6 divided by, in parentheses, 25 NCR 12. Right? You could actually just plug that whole combination statement into your calculator, and then it'll just spit out 0.2021. You can try without parentheses. I don't know if it'll work or not. Not sure. All right. All right. Seem reasonable? Okay. This would be a, here, I'll actually go back. We could have actually, the one we did before, where we were looking at, I asked the question, like, there was, what was it? There was 36 Cokes and 24 lemonades, right? And the question, one of the question was, if you pick two, then what was the probability that you get one of each, right? Well, we did the probabilities, but when we were doing one of each, remember there was like two branches that we had to consider. But if you think of it as a counting problem, you don't have to worry about that because the tree diagram respects order. It's saying Coke then lemonade is different than lemonade than Coke. But combinations say those two branches aren't different, they're the same. And so if you treat it like a combination problem using the template that we just used, right? How many drinks were there total? 60. And how many were we picking? Two. And how many Cokes were there? 36. And how many do I want? One. And how many lemonades are there? And how many do I want? One. And so you don't actually have to draw out the tree diagram and realize there's multiple branches and you have to multiply them and then add them or whatever. You can do it as a counting problem and you can check, like 36C1 is 36, 24C1 is 24, 60C2 is, I don't know what 60C2 is. It's big. 1770. Okay, and then you get or you can put it all in your calculator at once. But what is 36 times 24?
864.
864, and then divided by 1770, and then round to two decimal places. I bet it's like, if it wasn't like 4882, if I remember right. 4881 if you round here. Is that right? Yeah, 4881. And then if you go back to our slides and you look back at the Coke lemonade example, that's exactly what we got. Well, we were off by a 10,000, but that's just a rounding error. But this one's actually probably more accurate. This is a more accurate number because in the other one we rounded twice and then added them. But in this one we're only rounding once at the end. So if you can frame a probability problem as a counting problem, it actually makes things simpler. So, yeah.
So doesn't the order matter for this one? The order that you picked does matter?
Well, at the end of the day, if all I care about is getting one of each, do I care if it comes... Like if I go in with two hands, does it matter if I'm holding the Coke in my right hand or my left hand? Doesn't matter. But see, the problem with the tree diagram is that the tree diagram treats it like it does. Right? Because the tree diagram says, oh, you got Coke then lemonade here, you got lemonade then Coke there, they're different. But in reality, in practice, I know they're not, and so that's why the tree diagram, it works, but it has some issues with it. You have to recognize that both of those are giving you what you want. Whereas the combination shortcuts it all and says, oh, I don't care about the order. I understand that both of those are the same things.
So instead of doing a tree diagram, can we technically just do NPR in that same format?
If it's a counting, right?
Like
If the order matters.
If order matters.
Yeah. If what's the probability? You're saying what's the probability that you get a?
Coke first and then a lemonade.
Yeah.
And then you're asking if you could swap out.
The NCR for the NPR in the calculator. I can just do the tree diagram.
Like Coke first, if you're going Coke first, lemonade second.
Yeah.
I want to say no, but well, I don't know. It's like it's not. It probably will work.
just do a problem like that so we can
Well, I'm trying to think. I don't even know.
Try one.
how to figure it out anyway?
I don't even know why you would treat it like a counting problem.
Kind of irrelevant. but-
What does this even mean? What is that? It's saying that's the number of ways that you can arrange one item out of 36. It's just 36. The number of ways you can arrange one item out of 24 is 24. Those don't change because 36C1 is the same as 36P1. Because you're just picking one item and you can't. But what is the bottom? 60P2, the number of ways that you can rearrange to. No, this is a different problem. This is actually answering a different question. This would be, because see, this is different. This is the number of ways to rearrange two cans out of 60. But see, a permutation, it treats every can uniquely. So it treats lemonade 1 as a different can than lemonade 2.
So it just adds way more.
Yeah, and then
Complexity.
right, and so this won't work. This is going to give you some really small number, I think, because what is 60p2? What does that number give you? Just out of curiosity. 60p2.
3,540.
3,540.
It basically half the chance.
Oh wait, it is working.
Yeah.
Yeah.
Yeah, I got half of 4.488 more.
Oh well,
I don't know.
why does it work?
I'm just getting class off track.
Why does it work? 60p2, that gives you all the ways that you could pick. Oh, I think, okay, maybe it does make sense because what does this number on top come out to be? That 36p1 is 36. It's the same on top. Okay. And actually, it makes so it's saying that there's 864 ways that you could get a Coke first and a lemonade second.
Yeah. And then
Yeah.
you divide by.
And so there's 864 ways that you can pick up, and you can see it says Coke here, lemonade here. And then you're dividing by, this is saying, well, there's 3,540 ways you could actually pick them. So actually it will work in that case. The thing I'm afraid of is,
There's more than just one.
I'm afraid of it won't work when you get into higher numbers than 1 and 1. The reason I think it works here is because 1 is the special case where the combinations and the permutations match up. But that doesn't happen once you go beyond 1. Because as soon as you allow yourself to pick 2, that's where you run into, like, if it was, what's the probability that you pick 2 Cokes first and then a lemonade at the end out of 3? Then I think, okay, it's not that relevant to the class. So we're getting way down the rabbit hole. See, that's the thing. Counting is really, really complicated,
There's
actually.
There's a lot of nuances.
Yeah, and so I think it's the special case that we're at 1 and 1 here, but I think it's going to get screwed up but I could be wrong. I might be wrong about that. I don't know. Would it work for more than that? Would it work for if you were drawing 3 and you wanted to figure out? See, that's the nice thing about combinations is that if you say you were drawing 3 Cokes or 3 cans.
Yeah, no, it doesn't work.
I don't think it works.
I got 196.
Yeah, so see, if you were drawing 3 cans and you wanted to go the tree diagram route, you have to now make your tree diagram way bigger. But the combination method would be really easy because it's like if you wanted 2 Cokes and 1 lemonade, you just have to update your numbers, and all of a sudden you can get using that template. So we got way down the
rabbit hole.
yeah, we kind of went a little off the rails, but it's interesting to think about. So, yeah. Counting problems can get very difficult, So, okay. Yeah. All right. Here's an example where it gets a little bit more complicated, but combinations help you. Okay. So let's say you have a batch of 100 TVs, okay, and they get shipped to a retailer. So, yeah, right. So the retailer, they want to decide whether or not to keep the batch or not because they want to make sure they're not getting a bunch of busted TVs. So they have to come up with some quality assurance process, but they don't need to open every single TV. That's going to be a waste of time and resources. So what they do instead is they just pick 2. So they pick 2 TVs out of the batch. If either of them are defective, then they send the whole thing back. And if neither of them are defective, then they keep the batch. Okay. Well, the manufacturer knows that they have a defect rate, obviously, right? You can't produce 100% perfect products. So let's say the manufacturer knows that 6 of their 100 TVs are defective. Okay. What's the probability that they're going to get caught and the shipment is going to get returned?
C6.
So basically, the retailer is going to do one of 2 things, right? The retailer is either going to accept the batch, or they're going to reject the batch. Okay. Well, what has to happen for them to accept the batch?
You have to find at least one.
That'd be to reject, right? So accepting the batch would be like what?
0.
Yeah. So to accept the batch, they have to be both good, or you could think of it as 0 bad. It doesn't really matter how you frame it, right? You have to think of them as both being good or neither of them being bad. Now, to reject it though, so it has to basically be like we could say like good, right? Now, what about rejecting it? To reject it, what could happen?
You just one bad.
Yeah, it could be that one of them is bad, or it could be they could both be bad, right? So like the rejection happens when either the first one's good, the second one's bad, the first one's bad, the second one's good, or they're both bad, right? Yeah? So, all right. And what's my question? My question is, find the probability of what?
The return shipment.
The return shipment, find the probability that they reject. Okay? Now, the thing is that there's 2 ways that they could reject it, but there's only one way for them to accept it. So how should we approach this problem?
Find the rate of acceptance and then just flip it.
Right. This is one of those examples where the complement actually makes more sense to calculate, because if I'm looking at here, this is 2 scenarios where they will reject, but there's only one scenario where they reject or accept. So in this case, another way to think of it is like, if you think about it as like a table, they're either going to find 0, 1, or 2 defects, and their decision is going to be either to accept, reject, right? So if I'm trying to figure out the probability of rejecting, I could do 2 probabilities and add them up, or we could think of this as this is our event R, and then this is our event complement. So to figure out the probability, so if you're trying to figure out the probability of at least one defect, right, it's a lot easier just to do the complement, and let's figure out the probability that they accept it and then flip it, like you said. Okay? So that's the way. So this is one of the times that the complement rule really comes in handy. If you're dealing with a complicated situation where the thing that you want to see could happen a lot of ways, but what you don't want to see is much simpler, you should calculate the much simpler option and then just do the complement probability. So what we'll do is we'll figure out the probability that they don't find any defects, and then we'll take 1 minus that. But this problem is not that different than what we were dealing with before. Because essentially I got a big group of things, and within that big group there's 2 subsets. There's bad TVs and good TVs, and I want to see a certain number of bad ones and a certain number of good ones. Okay? Because, so in other words, how many TVs are out there total?
100.
And how many are they going to choose? 2, right? Okay. Well, how many of them are bad?
6.
And how many are good?
94.
Yeah, so remember, those numbers got to add up. So if there's 6 bad ones, then there must be 94 good ones.
But you want 0 bad.
Right. And if I'm trying to figure out the probability that they keep my TVs, then I want to make sure, what I'd like to happen is for both of those 2 to come from which of these?
The 94.
I want both of those 2 to come from the 94 good ones. So if I'm the one sending them TVs, then that's 2, and I don't want any to come from there. Right? So then if you calculate this, so 6C0, that's going to be 1. Because how many ways can you pick nothing from 6 items? You can do it one way, just don't pick anything. You can plug in your calculator, it'll agree. If you do 94C2, what do you get?
Or 371.
4371. And then if you do 100C2, what do you get? $4950. Okay. So in the numerator, this is the number of ways to pick 2 good TVs, right? And this is just the number of ways to pick TVs. Okay. So then, well, what is 4371 divided by 4950?
8330.
8330. Okay. So that right there, this, I'll go a different color because it's getting kind of messy here, sorry. But this right here, this is the probability that they keep my TVs. Right? Because they keep my TVs when there's no defects. So then what's the probability they send them back? Well, it's 1 minus the probability they keep them. And so then the answer is 0. Was that 1?
1169.
Oh, 6, 7.
It was supposed to be 8830.
Oh, 8.
8.
Oh, 8, 8,
Yeah.
3, 0. Oh, I see. Sorry. So then 1 minus that would be 0.1, 1, 7?
It's not repeating.
Oh, okay, we'll just go, whatever. We'll go with that. So there's an 88% chance that they'll keep my TVs because that's the probability that they don't find any defects, which means there's about 11, 12% chance they're going to send it back. That make sense? And so thinking about these types of so the thing is that thinking about these is it becomes important because if you're the TV manufacturer, you have to decide, is that good enough, right? Like, am I okay with them sending back TV batches 11% of the time, or do I need to be more precise, or do I need to make better TVs? And then if you're from the retailer's point of view, you have to decide, okay, am I willing to accept that many bad batches, or do I need to change my quality assurance process because I'm accepting too many bad TVs or something, right? Okay. Yeah? Anybody tried the second quiz yet at all? Okay. There's a really interesting one like this on the quiz. By interesting, I mean it's hard, but it's interesting. There's an interesting one on the quiz about this, I think it's still on there. I think I left it on there. I'll have to look. But it's about why planes overbook flights. And it has to do with this, because there's a good chance that people don't show up. Okay, and it's about, how far can you overbook a flight before the probability of you having to bump people off the flight hits a certain threshold or something like that. It's an interesting problem. Okay? All right. Any questions about that one besides what the heck are we doing in this class? Okay, but the point is this is just the reason I give you this problem is to show you that the complement rule is very useful sometimes. And you can imagine this gets even more useful as the numbers get way bigger. Because if they're picking like 7 TVs, then there's a lot of ways that they could reject, but there's only one way they take them. And so I don't want to have to calculate a whole bunch of probabilities. I can do the same strategy no matter how many they're picking. So the counting strategies help a lot. All right. I don't want to do that one. This one is kind of interesting, though. It gives us a chance to use permutations, which we haven't used much. Okay? So this is sometimes called the birthday problem. Actually, how many people we got here today? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. It might work. The more people you have, the better. Okay, so do you think that 2 people in this classroom share a birthday? No. Do you think, does it seem highly likely that people could share birthdays, or highly unlikely, or somewhere in between? Maybe. Highly unlikely, some say highly likely, some... Okay, you could actually figure out the likelihood. Okay, so if you think about it, this is where our strategy is going to pay off with the complements again, because I want to know, okay, well, what's the probability that at least 2 people share a birthday in this room right now? That's what I'd like to know. Okay, and so I counted 20. Somebody else count up and include me, just to make sure we got the right number. Somebody count how many people are in here, including me. 22 with me?
Yeah.
22 with me. Okay, that's what I got. Okay, so then we say, okay, well, I want to know what's the probability that at least 2 people share a birthday. Well, that could happen a lot of ways. Like 2 of us could share a birthday, or 3 of us could share a birthday, or 4 of us could share a birthday, or 5. I mean, it's not likely, but it could happen. But the complement's a lot simpler. What's the complement of at least 2 people sharing a birthday? It's nobody shares, right? So what we'll do is we'll take advantage of that. We'll say, okay, we'll figure out what's the probability that no one in here shares. Dang, dude, I think I'm going to braid this bad boy. I don't know why he keeps doing that. Weird. Okay. Okay. So we'll figure out the probability that no one shares a birthday first, and then we'll go from there. Now, that's not exactly easy, but we can do it with counting. Okay. All right. So probability is a fraction. Okay. And on the bottom, it would be, the probability no one shares a birthday would be, well, first off, the numerator is going to be the number of ways that our birthdays could be arranged. Right? There's a lot of ways that us 22 people could have birthdays. And we're assuming that month day is unique, right? So we're not talking about like day of the month. It's like you have to have the same day and month, not year. We won't go by year. Okay. So number of ways that the birthdays could be arranged, and then on the numerator we got to figure out the number of ways that they are all unique. Right? Okay. So the bottom one is not that hard to figure out, because how many ways? Is anybody here born on February 29th of a leap year? Nobody? Perfect. So we can assume a year is 365 days long, right? Okay. So how many different days could I have been born on? And how many different days could you have been born on? And how many days could the person next to you have been born? And repeats would be allowed because we could all have the same birthday. It's okay. I mean, it happens. or wouldn't happen, but it could. Okay, so it's not really a permutation or combination problem. It's a basic counting rule problem, right? So it's like there's 365 ways my birthday could happen, times 365 ways your birthday could happen, times 365 ways another person's, all the way down to however many people. Yeah, so in other words, it's going to be 365 to the 22nd power, which is a huge number. Okay, that's going to be our numerator. Okay, now what about the denominator? Because what happens is, okay, my birthday could occur 365 ways, but then what about your birthday? If all of us have to be unique, once my birthday is fixed, what has to be true about yours? Has to be different. There has to be 364, right? And then once that we figure out that person's birthday, then the next person has less options, right? All the way down, until we hit 22 people or whatever. But this right here, this is exactly a permutation. This is 365 permute 22. Okay. And so, because it's like, how many different ways can you pick someone's birthday uniquely and rearrange them? Okay. And so the probability that no one shares a birthday, this is where knowing how to use the calculator well helps out. This is going to be the probability. And so in your calculator, just go parentheses 365 NPR 22, divide by parentheses 365 to the 22nd, and put parentheses around that. That way you can then you don't have to store the really big numbers. The calculator is stolen for it. It'll spit out decimal. So what does that come out to be?
How come it's not a combination?
It's not a combination because you're thinking about it, and you have to think about it. So it's like you could, if you the first person. Because if my birthday is January 1st and yours is January 2nd, that's different than my birthday being January 2nd and your birthday being January 1st. Right?
Why? I mean, it is, but
It's hard to like.
why does it matter in the numbers? Because we're just talking about any day.
Because we're treating it differently at the sample we're treating it differently at the denominator too. Because in the denominator, the way we're saying, like the number of ways that we have birthdays, me being January 1st and you being January 2nd is different than me being January 2nd and you being January 1st. Like those are different, aren't those different? Mm-hmm. Or like you being January 1st, well, if they match, it doesn't matter. But you know what I'm saying? Like, I don't, maybe I don't know how to explain that well, but I mean, you can see from the pattern that it is a permutation, because this is exactly how permutations work. They're factorials down to the point where you run out of people and then they truncate off the end. I just know it is a permutation off the top of my head, but I may have to think about it better. What does that come out to be, by the way, though? Did anybody get a number?
0.524.
524?
I got a different number.
Oh, you got something different? People are getting different numbers.
Maybe I did it wrong.
I got 5243.
5243?
Yeah.
Okay. I'm getting a lot of people telling me they got that. Okay. So I'm going to go with that. Okay. So this is the probability. So actually, in this case, it's like a 50% chance. So there's about a little over 50% chance that nobody in this room shares a birthday. But what does that mean?
There's a 47
Yeah, there's a 0.4757 chance. So it's almost like a coin flip. So it's almost just as likely that two people in this room share a birthday as if we flipped a coin. It's going to land on heads.
Does anybody have March 8th as birthday?
March 8th. Shall we try?
I
Why
wanna
not?
Find out.
We can figure it out. So now the thing is that you could, if you try this with slightly different numbers, like replace this with 30 and replace that with 30, and then redo your calculations, the numbers go up really fast. So like by the time you get like 40 people in a room, there's like almost 100% chance that someone in the room shares a birthday. But I don't know, we'll try it. So we can just go around and you say, just say your birthday, and then we'll see. And then if it's your birthday, someone say that's my birthday, and we'll go around and see if it works. This hasn't worked for me in a couple quarters because it's better with larger class sizes. So where do you want to start? Start up here, and we'll go.
June 29th.
March 8th.
March 14th.
No, December 22nd. September 9th.
September 9th.
February 15th.
December 13th.
August 28th.
August 28th.
December 2nd,
Ooh, that's close. I'm December 3rd. No December 3rds? Darn.
October 6th.
October 6th?
July.
July 1st? But yeah.
August 7th.
August 7th?
March 31st.
Oh, we're running out.
April 11th. October 13th.
August 10th.
August 10th?
January 27th.
And then over here. What's your birthday? I'm sorry, I don't know your name, but what's your birthday?
October.
October what?
18th.
October 18th?
October 2nd. December 20th.
Darn.
March 25th.
We didn't make it. Not in this room. But it was less than 50% likely, to be fair. So really what we need to do is when people come in for a test, we just need to figure out. Because there's a high likelihood, because if you bump this up to 30, which is the enrollment in the class, and then if you include me, it'd be 31. Redo that calculation with 31. And tell me what you get when you bump it up to 31.
0.26,
0.26 basically.
95.
2695, which would mean that there's a 0.7305 chance for class-wide. So if you count me, and if everyone came into like our test, then by the time we add those extra 9 people that will show up, then actually the probability would go up. And then if you bump it up to like 40 people, by that point you're almost guaranteed that people share birthdays. So it makes a good bar bet
Yeah.
if you're ever in a group of people. If you're ever in a big group of people, and and then you could bet someone that 2 people in the room share a birthday, and you're probably right. It's a good bet. You should take the bet. But anyways, all right. So the point though is that you can tackle really complicated probabilities if you have counting strategies, because that unlocks the key. That's the key to figuring out how complicated events, how many ways they can happen. So, anywho, that's all I got for this module. I had this probability thing. I know probabilities can be kind of complicated. So what I was gonna do is, you can stick around and work on it today if you want.